And we are now recording. Let's get slideshow brought up. I think. Okay. Now, before we get started on that, though, these announcements you've basically heard before, but just to make sure you're aware of them. The Lawson State College Transfer Fair Day is coming up next Wednesday on the Birmingham West Campus. That's in the academic building. Get your name, please. Huh? Or? Okay, Jamal. Yeah. Remind me. Huh? Yeah, exactly. Right. Okay. All right, good deal. Anyone else who's come in since the call roll? Okay. So, coming up next Wednesday, 1 week from yesterday, in Birmingham West Campus, Academic Building, B Hall, from 9:30 to 11:30, the College Transfer Fair Days. They've invited a whole bunch of schools, and I bet you a lot of them will be here. Mostly universities. Just about everything in Alabama looks like they've been invited, and many in Mississippi, Kentucky, just all over the place. So please stop by now. A week from today, Thursday the 13th of February, they'll be here on this campus in this building. Okay? They say in the campus cafeteria, this is again 9:30 to 11:30. I don't see how the cafeteria is going to work. I think they mean the faculty staff dining room, which is a little bit, I don't know if it's any bigger, but at least people won't be eating breakfast and lunch at the time, and more tables will be available. May spill over into the hallways or somewhere around there, but go down in the cafeteria area and you can see them there. Please go by and pay a visit, even if you're maybe not planning to transfer anytime soon. Just get an idea of what it's like to do what they're looking for, information, scholarships, whatever they have available. And they're usually pretty generous. Huh? Grant. Okay. Great, right? Okay. Now, so that's next Wednesday and Thursday, the College Transfer Fair Days. Okay. And then coming up, a deadline coming up, but you can start the process now, the 10-week summer internship at either University of Illinois, University of Arkansas, or Howard University. Fantastic opportunity for undergraduate students to be exposed to academic research in the fields of mechanical, electrical, and material engineering. Incredible learning experience. How much does it cost you? They pay you $5,000 for those 10 weeks. That's not bad. $500 a week. I don't know if they pay it that way, but a $5,000 stipend. They give you free housing, which usually includes a meal ticket, so free food too, and they give you airfare there and back once, okay? So, fantastic opportunity. If you want to be a part of it, this is the time to start getting your package together. Now, on this, the email, they said application deadline was February the 15th, which was a little suspicious because that's a Saturday. In the brochure, they say February 17th, which makes more sense, that being Monday. So please get your, if you're interested, get the application in. Now, something else happened Tuesday, and then again on Wednesday. The Wednesday thing didn't affect anybody here, but the Tuesday thing did, okay? Every day at the end of the day, I put in the attendance. We were required to put in attendance. And, of course, on Tuesdays and Thursdays, I'm in class almost all day long until 5:45 in the evening. So sometime after that, I started putting in attendance. Now, Monday's attendance went in fine. That was Monday evening. or afternoon. But then when I was doing Tuesdays, there were two really major problems. Okay, one really major one, for me, I thought anyway. None of my attendance I had put in all term was indicated for this class. You see on the thing, they're green when you haven't put them in. They turn beige when you put them in. All of them, they turned green again. And they had all been beiged up to the point. Okay? And I said, what's going on? Went and opened the first one. And one person, okay, had been all their attendance removed. Okay? I thought, what is going on here? I had a suspicion I knew, but I wasn't certain. So I had to go in every day from the beginning of term and put that person's attendance back in. Okay, I got that done. And then when I started putting in Tuesday's attendance, I noticed two people were missing from the roll. And then I knew exactly what had happened. What had happened was, yeah.
People young like you should come to class.
What's that?
People young like you should come to class.
You think I should count? I didn't hear the first one.
I said people young like you should counsel class.
Young like me?
Yeah.
He's wipe it off. Okay, never mind. All right. Kwame is here. No, that's old fogies we get stuck in. Right. Okay. What I was saying is, when I did the attendance and then I saw two people were missing, I said, yep, I think I know what's happened. They've removed all the unpaid students. And evidently that one student paid after they removed them, so they had to put them back in, but of course they had wiped out all his attendance. So I still have two people who, as of Tuesday, it indicated you hadn't completed payment. Now one of them's here and one of them's not, so I'm preaching to the choir. That's why I have the recording on now. Hopefully that person will hear and get the payment completed. Otherwise, you're out of the class. So please get that taken care of immediately, if not sooner. I don't know how long of a window they'll give you, but please get the attendance. Get your payment made. And also tell any of your friends. If anyone has trouble logging into the system, hey, I can't get in my class. That's why you can't get in your class. And it may be something as simple as all your tuition and fees were paid except for your insurance. And you didn't know that. And if the insurance wasn't paid, they kick you out of class. Okay, so please get all the payments taken care of. Okay? Because don't want to lose you. All right, that took too long probably. Let's move on here. First, any questions from anything we've covered so far? All right. We're in Chapter 1, Functions in the Graphs, 1.6, a library of parent functions, and we were just about to get going on step and piecewise defined function. And the bizarre thing is I'm covering the same thing in a calculus class, so I thought, we've already done this, haven't we? I said, no, that was in the other class. All right. Functions whose graphs resemble a set of stair steps are known as step functions. The most famous, and I don't know what makes it so famous, of these step functions is the greatest integer function, which is denoted by this symbology. Did they go over this last time? We did not. Okay. What's that? Right. Okay. But the same author has almost the same slide in that other book, so it just looks so familiar. Here's how you indicate the greatest integer function. It's kind of a double bracket around the function, okay? And that means f of x is equal to greatest integer in x is how you read that. The greatest integer less than or equal to x, okay? So let's do a few. What would it mean to be the greatest integer less than or equal to negative 1? Greatest integer less than or equal to negative 1. one integer that's equal to negative 1, isn't there? Negative 1. So that's the answer there, okay? Negative 1. Greatest integer less than or equal to negative 1. How about negative 1/2? Okay? Less than or equal to, you're absolutely right, that's also negative 1. Now, how I do it, or picture it, picture the number line, okay? Find the number you're looking for on the number line, negative 1/2. That would be right here. Well, the greatest integer less than or equal to negative 1/2, sure enough, is negative 1. You have to look to the left, less than or equal to, that's going to be, greater than or equal to, less than or equal, greatest integer in, less than or equal to x. So you look to your left, and that gives you a negative 1. Now, when you're on the positive side, it's really easy. If this had been, say, positive 7.5, you just throw away the half. The 7 will work. 8.25, throw away the decimal, the 8. But when you're on the negative side, looking to the left, you go down 1. So this is negative 1/2, it goes down to negative 1. Okay? So that's how you do it. It's a pretty easy thing to do. Okay? How do we graph that? How does this look? Okay? Oh, here's some more. Greatest integer in 1/10. Less than or equal to 1/10. Say again? 0. Perfect. 1.5. 1. Just throw away the 0.5. 1.9. 1. Throw away the 0.9. Okay? That's how you do these. Just remember, you don't do that on the negative side. If that was negative 1.5, what would that have been? Negative 2. Negative 1.9? Negative 2. Look to the left to find that next integer. Okay? So here's how we graph it. Because the value itself, like negative 1, is negative 1, and then anything greater than negative 1 is also negative 1, up until you get to 0, and then it jumps up to 0, because that greatest integer in 0 is 0. And then anything between 0 and 1 will still be 0, until you get 1, then you jump up to 1. Okay? And you just keep doing that. Okay? The left-hand endpoint is included, right-hand endpoint is not, because you jump up to the next level. And now you see why they call it a stepwise. That looks like you're climbing a step. Okay? Greatest energy function. Now, what's the domain of this function? All real numbers. What's the range of that function? All integers. Because 0.3 is not in the range. Only your integers. Negative 4, negative 3, negative 2, negative 1, 0. The only thing in the range are your integers. Okay? The domain is a set of all real numbers. Your range is a set of integers. Positive or negative integers. Okay? Does this have an x-intercept? Everything between 0 and 1 except 1. So how would you write that? Bracket 0, comma 1, parentheses. Perfect, because it does not include the 1. So there would be your x-intercept. So the infinite number of them. Between 0 and 1, counting 0 but not counting 1. Okay, how about y-intercepts? 0, 0. Certainly, that's it. Okay? Increasing, decreasing. Ooh. It's increasing at the integral values, but it's constant between the integral values. So that's sort of rather weird. Okay? All right. Can't think of many others. Let's see if they thought so. The range is a set of all integers. The graph has a y-intercept at 0, 0. The x-intercepts are on the interval from 0 to 1. Bracket 0, 1. Now you see why I don't really care for interval notation that much? That almost looks like the interval from 0 to 0. It's not. That's the point. This is an interval. Well, it gives it away because it's a bracket. But if that had been open parentheses 0, 1, that would have looked like a point 2. But it isn't. So you have to be careful. That's the point. This is an interval. Okay? The graph is constant between each pair of consecutive integers, but is increasing at the interval value. Jumps vertically 1 unit at each interval value. Okay? Now, you can do all sorts of other things with this, like put other functions inside the greatest integer function. And I think they'll show you an example of it. Now, to me, they say it's the most famous, okay, whatever that means. I didn't know they were very famous. There are many stepwise functions that you use basically very frequently. Has anyone ever mailed a letter? Yes. Okay? And most of the time those letters are between 0 and 1 ounce, right? So you pay your whatever fee that is. But if it's more than an ounce, it goes up. And it's good for another ounce, between 1 and 2 ounces. It's at that level. But then once you pass 2 ounces, it goes up again. So anytime you mail packages, mail letters, mail anything, you're using step function. Okay? Because it's one thing, one value for some interval of your domain, and then jumps up another value for the next one. Okay? Some of the old cell phone plans used to be this way. You might get the first 100 minutes, 500 minutes, whatever, at one rate, but then if you use more than that, it goes up. Or data minutes or whatever, you know. Check them out. I bet you some of your plans may still have stepwise defined functions. You don't pay attention to them probably, but they're still there. Okay? So let's do example 2. Okay? Evaluate this function, f of x is equal to greatest integer in x plus 1 for these 3 values. Okay? Now, the first one at x equal 1. Okay? Let me get my pen set up. If it'll set up, there it goes. F of -1 would be what? Tell me how to write it. What does that mean? F of -1. Greatest integer in -1 plus 1. And what's the greatest integer in -1? -1. Plus 1 is 0. That didn't give you much, did it? How about the next one? F of 2 would be what? Greatest integer in 2 plus 1. What's the greatest integer in 2? 2 plus 1. Pretty easy so far, isn't it? That's 3. But how about this next one? F of 3/2. What would that be? Greatest integer in 3/2, which is, you're absolutely right, 1, because that's 1 1/2, plus 1, and that would be 1 plus 1, and what's that? 2. Didn't know you'd be doing such high-level math today, did you? 1 plus 1 is 2. Have y'all all got it? Good deal. Okay. Any questions? Does that make sense? I sort of wish they'd have given you, if that had been a -3/2 rather than positive 3/2, what would that have been? If that was a -3/2 here, a -3/2 there. Second, -2 plus 1 would be -1. Perfect. Okay, y'all got it. Way to go. Any questions on this? Okay, there is a checkpoint right after every example. Please do those as soon as you can after class. If you can't remember how to do it, there is an audio-video solution at larsonprecalculus.com. Absolutely free website. Let's see how they did it. Let me erase this. Okay. For x equal -1, the greatest integer less than or equal to -1 is -1. So f of -1 is absolute value of -1, not absolute value. Greatest integer in -1 plus 1, which would be -1 plus 1, which would be 0. Y'all got it. Nailed it. Okay, same thing for x equal 2. Greatest integer less than or equal to 2 is 2. So f of 2 is greatest integer in 2 plus 1 is 2 plus 1 is 3. Perfect there. Okay. Second? Yeah, I was trying to find your name. Couldn't remember your last name. I was looking for your first. Okay. Got it. Anyone else come in since I called roll that can get in here and call you name? Okay. We're doing example 2, bottom of page 63, chapter 1, functions in the graphs, 1.6, a library of parent functions. Okay. Remind me? Stinson got it. Jemiah. Does anyone else come in since I called roll? Okay. We're on, in chapter 1, functions of the graph, 1.6, library of parent functions, page 63, bottom of the page, example 2. We're just done the second part of example 2. The third part is for x equal 3/2. Name, please.
Children.
Okay, got it. Anyway. Sorry. The greatest integer in 3/2, so the greatest integer in 3/2 is 1, because the greatest integer less than or equal to 3/2. 3/2 is 1.5, so the greatest integer in that is 1. So the f of 3/2 would be the greatest integer in 3/2 plus 1, and that would be 1 plus 1, which of course is 2. Okay. Everybody got it? Okay. Any questions? All right. Verify your answers by examining the graph of this. Now, we haven't talked about how to do this, but we will get to it. But notice this graph is different from the last one because your function here has 1 added to it. So as before, this line right here was down here. It jumped up 1 because you added 1 to it. This line right here was over here, and because you added 1 to it, it went up. Every one of them went up 1. And then you can verify all those that you looked at. -1 was 0. 2 was 3. And 3/2, 1.5 was 2. Okay? So you can check it there. And again, there is a checkpoint. Please do the checkpoints as soon as you can after class. All right. Now, before we do the parent functions, there is an example 3 that they didn't do on the slide set, so let's us do it here. Okay. And this one, you can go to larsonprecalculus.com for an interactive version of this type of an example. Same place you go for your checkpoints. Here you can hear them talk about how to do this. Here is another piecewise defined function, but it's not a step function. Here is the graph. Well, here is the function. F of x is defined to be 2x plus 3 when you're less than or equal 1, and it's -x plus 4 when you are greater than 1. Okay. Now, how do you sketch the graph of one like that? Okay, let me tick off a few points here. Okay. Pretty ugly graph, but you'll see. Okay. Now, how would you go about graphing that function? Piecewise defined function, but not a step function. I don't know how you learn to graph. Many teach it to do a T-table, right? You remember that? If you like to do that, you certainly can. I kind of like just to pick values. You know, it's sort of like a cheerleader. Give me an X. Huh? 2, okay? Now, first thing you ask yourself, where are you, Waldo? Is 2 less than or equal to 1 or greater than 1? Greater than 1. So you're down here. So negative 2 plus 4 is 2, okay? So when X was 2, Y was 2. Okay, there you are. There's the first point. Give me another X. Say again? 3. Okay, where are you? Down here again. So negative 3 plus 4 is 1. Okay, got that one. 3, 1. Okay, give me another X. Negative 5. Is that what you said? Where are you, Waldo? You're in the top one now because you're less than or equal to 1. So negative 5, you plug that in here, that gives you negative 10 plus 3 would be negative 7. Is that what you said? Good. Negative 7. So negative 5, 1, 2, 3, you got me off scale. Okay? He did it on purpose too, by the way. Okay? Fire him. Okay, never mind. Okay? Let's go on not quite as far as negative 5. Negative 1. Let's do negative 1. That's certainly less than 1. So 2 times negative 1 is negative 2 plus 3 is 1. So negative 1, 1. That will be 1. Okay, there we are there. Let's do another one. Give me another X. 0. Oh, I like 0. Where are we, Waldo? Top or bottom? Top. Okay, because 0 is less than 1. Okay, and you put a 0 in here, and what do you get? 3. Okay, 0, 3. Yeah. There you are right there. Okay? Now, do you need some more, or you got an idea where this is heading? Okay? Here is another, I consider a little bit easier way to do this. It's easier because of the type of functions these are. What kind of function is this one? Again? The only exponent is 1. What kind of function is that? Oh my goodness. That was a long time ago, like Tuesday. Okay. What kind is it? Maximum exponent. The only exponent is 1. What kind of function was that? Linear function, right? Straight lines, right? Now this one would have an intercept at 3, wouldn't it? 2x plus 3. Of course, it doesn't go as far as 3, but that's where it would be headed. Plus 3. Hey, we just found it. It did go that far, okay? And a slope of 2, we had that one. Another slope of 2 would be about here. Another slope of 2 would be about here. So here is that function. If I had drawn a good graph, it would be easier to do, but I didn't draw one very well. It goes right up and includes 1. So if you go up another 2 for 1 over, it includes that point right there. So here is that function there, right? Now the other one is also what kind of function? Linear. What's its intercept? If it went there? 4. What's its slope? Negative 1. Of course, it can't get to 4 because it has to be greater than 1. But if it did, 1, 2, 3, 4, right there, I'm going to put a shadow intercept there. It doesn't really get there, okay? In fact, it gets up to 1, but doesn't quite get to 1. But the slope is down 1, right 1, okay? Right 1, down 1. It would be right there. It doesn't get there, though, because at 1, you're up here with this function, right? But it goes right up to it. And sure enough, there would be the function. Straight line, if I could draw a straight line. Now, treat it as if it did go to 1, but just put an open circle there. And then it goes right up until that. This one, put a closed circle because of that equal sign, right? So you just graph this one with an equal sign at 1, with a solid circle at 1 because of that equal sign. Do this one, go right up to 1. In fact, put 1 in here. That would be -1 plus 4 is 3. There it is. But put an open circle because it doesn't include 1. Does that make sense? That's how you do piecewise defined functions. Pick some points, get on it. At the endpoints, put them both there. The one with the equal sign, make it solid. The one with no equal sign, make it open circle. Again, goes right up until that open circle. Make sense? If you look at the book, their picture's almost as good as mine, don't you think? You better say yes. Okay, good. All right. Good deal. Any questions? And by the way, there is a checkpoint, so I would certainly do the checkpoint. And in fact, if you're not understanding what I'm doing here, go to larsonprecalculus.com and see interactive version of example 3, and then you do its checkpoint. All right. Any questions? Piecewise defined functions, how you graph them. Okay? And let me tell you this, as much emphasis as this book puts on graphing, you better believe the test bank puts emphasis on graphing too. Oh, you got the quiz already. There's what? At least one graph on that quiz. Okay? And you'll see that on every test, every quiz, basically. All right. So let's now go to the parent functions. These are the ones who stay up late at night waiting for the... No, never mind. Okay. So here are 8 graphs. 4 are shown here. We'll go to the next slide and show the other 4. These are our most commonly used functions in algebra, at least the simplest version of the most common. Here's the constant function, okay? Alpha of x equals c, okay? Remember we did that. We've shown it before. It has a y-intercept, not necessarily an x-intercept. Its slope is 0 because mx plus b, the m is 0. That's why you don't see the mx in there. So this is, the function is always c. This looks like this would be about 1.2 or something like that. Always there. No matter what the x value is, the y is always c. Okay? Then we have the identity function. Okay? Alpha of x, which is, what's alpha of x always equal to? Y. Y is equal to x. They're identically equal. So if this is 1, 1, 0, 0, 2, 2, negative 1, negative 1, negative 2, negative 2, they're the same. That exactly bisects the first and the third quadrants. Okay? That's your identity function. Now that's also, both of these are samples of what other kinds of functions. Linear function. A generic linear function that's not either constant or this one could be any place else with any other slope. So you have an mx plus b, where m doesn't have to be 1 or 0, and the b doesn't have to be 0, or c here and 0 there. Okay. Now, I don't think we did this, but they want to remind you of it, the absolute value function. This is a piecewise defined function. Because the absolute value means that the y is never negative. Okay? So absolute value of x means the value of x without a minus sign. So for positive x's, that's just like your identity function. Y is equal to x when x is positive. Okay? But when x is negative, you take this from here and flip it up here because your absolute value is never negative. So this is your absolute value function. It's a V-shaped function. Okay? is the only one of these that they say is not smooth. Now, we haven't talked about smoothness yet, but it's not. That's a smooth function. That's smooth. That's smooth. This is not smooth. Okay. Absolute value function. Square root function. Interesting, they do square root before they do the squaring function. I don't know why. But that is your half of a sleeping parabola, remember? Okay? 0, 0, 1, 1, 4, 2, you know, just keeps on going. Square root function. Not defined for negative numbers because you can't take the square root of a negative number, and because that's the principal square root, the y values, the range is also never negative. Okay? This one I thought we were going to do next. This is a squaring function. This is a parabola. Okay? Intersects at 0, 0, like many of these do. But later, a general quadratic function will look like this, but could be anywhere on the graph that way, this way, anywhere on it. It can be skinnier, thick, yeah, whatever. Here's your cubic function. Again, 0, 0 is both the x and y intercept. That comes up as if it's going to maximize here, but then it doesn't. It sort of flattens out, but never exactly flattens out, and then starts always increasing. Okay? A generic cubic function will actually typically have two humps, one negative, one positive. Just like you separate these two and go down in between. Here's your reciprocal function in its simplest form. If you negated that, it would be in these quadrants. Okay? If you, well, you do all sorts of other things too. All right, and then finally, your greatest energy function is one type of a piecewise defined function. That's the one we were just doing. Okay? You have other piecewise functions. You could have one piecewise function that looks a little like this up to this point, and then a linear function after that. I mean, you can do all sorts of things with piecewise functions. Familiarity with the basic characteristics of these simple graphs will help you analyze the shape of more complicated graphs. In particular, graphs obtained from these graphs by rigid and non-rigid transformations. That's what we're going to hit in the next section, which is coming up very, very soon. Just like Jay is coming up right now. Okay. Anyone else coming since I called roll? I've been talking to the board, so I may have missed you. Okay. That's the last slide in section 1.6. Vocabulary here. The first 9 is write the most specific name for each of these functions. All right. The first is f of x is equal to an x inside a double bracket. What's the name for that? If I read it to you, I'd give it away. Say again? You may have said it right, I just can't hear well. F of x is equal to x inside double brackets. Greatest integer function, you got it. Number 2, f of x equal x. Identity function, perfect. Number 3, f of x equal 1 over x. Reciprocal function, excellent. Number 4, f of x is equal to x squared. The squaring function, I almost gave it away. F of x is equal to an x inside of a squirrely little house looking thing. Square root function, perfect. Okay, f of x equals c. Constant function, good. F of x is equal to x inside 2 vertical lines. Absolute value function, you got it. And then f of x is equal to x with a little 3 as a superscript. Cubing function, cubic function. And f of x equal ax plus b. Second? ax plus b. Second? It's not step. ax plus b. If I said mx plus b, would that give it away? Huh? Okay. Yeah, well, what was the name of the function, though? Linear function. The maximum exponent is 1. The only exponent is 1. All right. Then number 10, fill in the blank. The constant function and the identity function are two special types of blank functions. Same thing we just said. Linear functions, perfect. Okay, homework exercises here, either 11 or 13. They're both at Calc Chat. 11's at Calc View. Any of the odds, 15 to 25, they're all at Calc Chat. 27 or 29, they're both at Calc Chat. 27's at Calc View. 31 or 33, they're both at Calc Chat. 31's at Calc View. Any of the odds 35 to 39, they're all at Calc Chat. 35's at Calc View. Do 41 is at Calc Chat. And then you get a choice of any of the odds 43, 45, or 47. They're all at Calc Chat. Then there's a true-false, 49. This also should be at Calc Chat. Any questions on 1.6? Now, is anyone here who did not get the quiz last time? Okay. Okay, hang on a minute and let me get to them. All right, I'm almost there. Now I'll have a question for you, whether you need graph paper or not. Okay? Who needs one? Need graph paper? Okay? Need graph paper? Need graph paper? Need graph paper? Who else? All right, need graph paper? Okay. Anybody else? Nobody else got quiz 1? All right, quiz 1 is technically due 1 week from today. I gave them out last time to let people have a head start on it. 2 reasons I give you at least a week to work on the quiz. First reason, if you have any questions, you can ask me on the day in between, like next Tuesday. Okay, second reason, always gives you a weekend to work on it. Okay, in case you work during the weekend, you don't have much time. All right, now, if you need more time than that, you can certainly have it. But you've got to turn in quiz 1 before you can take test 1. If you don't, you have to ask me very politely to give you a 0 on the quiz. I don't want to, but if you ask me politely, I can't refuse. Okay? So, my advice to you, get it in way before test 1 so I can get it graded and you can see if you missed anything. Okay? Because I don't want you making the same mistake on the quiz and the test, and if you turn it in the day of the test, then take the test, you don't have a chance to see if you missed anything. So please get it in way before the first test comes around. Shoot for 1 week, but if you need more time, you can have it, but get it in well before the first test. And you'll know when the first test is coming. Okay? Now, I can't return the quizzes to you until everyone turns them in. So if you got a slow classmate who's dragging down the class, give them a good kick. Oh, no, I can't say that, can I? Okay. But, encourage them to get their papers in so you can get yours back. You can always come see me and I'll show you what you missed, but I can't return them to you until I get them all in. So don't be the person who holds up the whole class, okay? Get them in. All right. Any questions? Good deal. Okay. Okay. So that ended 1.6. Let's move on to 1.7. And the very last slide in 1.6 is a good lead-in for what we're going to do in 1.7. You ended up with the parent functions, which are simplest functions of every type. And then what we're going to do is start working on how you change those functions. Okay? And the book is really big on this too. I don't see it's quite that big a deal, but they really love it. So get used to it. Still in Chapter 1, Functions in the Graph, 1.7, we're going to start transforming functions. You have the basic parent functions. Now we're going to start manipulating them. Fiddly. Yeah! Thank you. What? Yeah! Just got to make sure y'all are awake. Okay. That's part of my job description. Okay. All right. So 1.7 is transformations of functions. We're going to start fiddling with the functions and seeing how we can change them and what those changes do to them. Okay. So the first thing we're going to do is talk about shifting the functions. We're going to talk about vertical shifts, horizontal shifts, and how those help us sketch the graphs of functions. Then we'll use reflections to sketch the graph of functions, either across the y-axis, the x-axis, sometimes the origin. And then, these are what we call rigid transformations. They use that term on that last slide. And then we'll use some non-rigid transformations to sketch graphs of functions. These stretch it or shrink it, okay? Either vertically or horizontally, okay? So let's start with those shifting graphs, okay? Many functions have graphs that are transformations of the parent function. For example, you can obtain the graph of h of x, which is x squared plus 2. Does anyone see a parent function in there? The x squared, that's the squaring function. So start with that, okay? And then every value for x that you put in here, and you square it, then add 2 to it. So when you square 0, you get 0. Add 2, you get 2. When you square 1, you get 1. Add 2, you get 3. When you square negative 1, you get 1. Add 2, you get 3. And so on and so on. What have you done? You shifted this original graph up 2. Okay? And that's exactly what it says you're doing. Because this was a y value, you're adding 2 to a y value, so that's a vertical shift. Because the y's are always on the vertical axis. So you've shifted the graph of f of x equals x squared, the parent function, up 2 units. So that's a vertical shift up 2 units, as shown here. Does that make sense? Pretty straightforward, right? All right. Now, I want to make sure I'm not skipping anything, okay? In function notation, h and f are related this way. H of x is equal to x squared plus 2, but your f of x, remember, is your squaring function, so this is f of x plus 2. So you got your f of x and gone up 2. Upward shift of 2 units. Now, this one you're adding 2 to a y value. That was y, right? Added to upward shift. Now we're going to add or subtract 2, or any number, from your x value, okay? But if your parent function is still your x squared, to change the x value, you have to get inside the parentheses. This is the x minus 2 squared. So this is going to be shifting horizontally. But here's the problem. Here, a plus went up, right? Guess what a minus does here? Remember, you're horizontal. So which way you go? You go to the right. You would think you went to the left. No. Catch this. Everything you do with x seems backwards. Okay? Just remember that. Everything you do with the x seems backwards. A plus 2 went up. A minus 2 goes to the right. Oh, why? Okay? By shifting the graph that way to the right 2 units is shown here. Okay? Now, this will make it seem a little more real, perhaps, because when you put a 2 in for x, g of 2, g2 minus 2 is 0 squared. that's shifted over this way. So you see that the 2 for x shifts it 2 to the right because of that minus 2 there. The other one, the plus 2 went up, the minus 2 here goes to the right. Same shape, non-rigid transformation, you just shift to the right 2 units. Okay? That's called a horizontal shift. Remember, always goes backwards from what it seems. A minus goes to the right, a plus would have gone to the left. Okay? Vertically, a plus goes up, a minus goes down. Okay. Any questions on that? All right. In this case, the functions g and f have the following relationship. G of x was x minus 2 squared, so that was f of x minus 2. That means it's a right shift because the minus is right. When you're dealing with x, it goes backwards 2 units. So the following list summarizes this discussion about horizontal and vertical shifts. Okay? So we're going to let c be a positive real number. Okay? Any positive real number. Fraction, decimal, rational, or irrational, it doesn't matter. Okay? C, a positive real number. Always positive. Vertical and horizontal shifts of the graph of y is equal to f of x are represented this way. Vertical shifts, c units up, what would that be? If your function is f of x, what would that be? F of x plus c, perfect. A vertical shift, c units down, if c is positive. F of x minus c. A horizontal shift, c units to the right would be f of x minus c. And a horizontal shift, c units to the left would be f of x plus c. Perfect. Perfect. Does everybody see that? See that? See that? Okay, never mind. All right. That's bottom of page 67. Let's move to okay. Oh, here's even nearer the bottom of 67. I was trying to find the slide. Some graphs can be obtained by combinations of vertical and horizontal shifts, and that's what we're going to see in example 1b. We haven't gotten there yet, but we will. Vertical and horizontal shifts generate a family of functions, each with the same shape but different locations. Okay? We call those rigid transformations. They just move around but don't change the shape. Okay? Now, we're ready for example 1. Use the graph of f of x equal x cubed, our parent function, to sketch the graph of each of these functions. Okay? Now, what I'm going to do is get my pen set up. Okay? Okay. Okay. Let's first graph f of x equal x cubed. Give me a few points. 1 what? 1 for x, what would be your y? 1. 1, 1. 1 cubed is 1. Give me another x. Say again? Did someone say 4? Is that what someone said? 4 cubed is 64. That's going to be way off scale, so let's not use 4. Give me another x. Say again? 2. Okay. 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. Barely got on there. 2, 8. That's as far as we can go to the right. Where might we choose to go? 0. Okay, what's 0? 0. Perfect. Something else to the left. -1 would be? -1 cubed is? -1. Perfect. And -2 cubed would be? -8, just like +8 before, only it's way down here. I can't draw it on the scale. So basically, get out of there, okay? It's a function that goes like this in this direction. I mean, goes way down here and like this in this direction, going way, way high. So there's our parent function, the cubing function. Now, I may not have it flat enough around 0, but, you know, we can live with that. Okay. Now, what do you reckon the A one here is doing? I need you to pick me a color. Blue? Is that what I heard? Okay, I've got Carolina blue and I have medium blue. Carolina blue, okay. All right. Good basketball color. Okay, never mind. I won't say that. Okay. Now, what is G doing? G is going to be my Carolina blue. What is G doing to F? Anybody? I was just doing so well on the previous slide, the very same thing. What in the world is G doing to F? Down 1, okay? So every one of these black points here, we're going to go down 1 and produce a Carolina blue point, okay? Every one goes down 1, including the one I can't get to. Okay, so this one will look like, get out of there, okay? This one will look like going down here, going up here. All right, there's what it did. Shifted down 1 unit, -1, to the functional form here. Okay, because it's a vertical shift down 1. What is H doing? Oh my goodness, what is H doing? Oh, I need a color. Before you answer that question, I need a color. Say again, green, is that what I heard? Okay, light or dark? Dark, okay, we'll go with green then. Okay, so H is going to be dark green. What is H doing to our F function? Okay, I heard right 2 and up 1. I'll agree with one of those, but not the other one. Left 2 and up 1. Okay, just don't say yours. Okay, never mind. Okay, okay, left 2 and up 1. Right? Is that what you said? That's what I did with my 0 for my 1 here. Go back to the black. Go back to the parent function. Go left 2 and up 1. Then for this one, I go left 2 and can't go up 1. So, but this one down here, I go left 2 and up 1. Okay, still can't get to that one. So here's what it's doing now. Going downhill fast here and up here fast here. Ooh, that's pretty ugly. But you see, I've taken this basic shape here and just shifted here or shifted here. This is both a horizontal and a vertical shift. Left 2 and up 1. Pretty ugly graph, but we'll see a little bit better one when they do it. Okay? Does everybody see what we did? Okay. Now, you could have started at the very beginning and done a t-table, give me an x, and then plugged in x's for each of these, and then drawn the graphs. So much easier just to shift the existing graph that you knew what it looked like. Okay? So let me clear these out of the way. Okay? And relative to, here was our parent function, the cubing function, f of x. The g of x went down 1. Everything went down 1. Okay? And there it is. Same shape, just shifts down one. Toward the end, they get really close together, and here they're pretty far apart. Okay? In reality, though, it's always the same. You're always one lower. Always. Okay? Just makes them look closer together because of this. Okay. Make sense? Okay? That's what we did too, right? Now this one, we're going a left shift 2 units and an upward shift 1 unit. So here's that same cubing function. And you went left 2, up 1. Okay? And there it goes. Make sense? Exactly the same shape, you just translated it. A horizontal shift 2 to the left and a vertical shift 1 to the upward. Okay. Now get used to both the verbiage, how it looks, and where it came from. I'll give you a hint, and you're going to see this on the next several quizzes, tests, and everything. They will either give you the function, and then you tell them, just like it tells you here, what it's doing. Or they tell you what it's doing, and then you write the function. Sometimes there'll be both of those. So get used to what these things mean. Okay? Be able to go back and forth either direction. Hint, hint. Okay. There is a checkpoint that has probably both a shift and a double shift. Okay. Any questions on example 1? Please do your checkpoints. Now, in example 1b, you obtain the same result when the vertical shift precedes the horizontal shift. It doesn't really matter, okay? We said go left 2 and up 1. If you're going up 1 and left 2, you wind up at the same place. It doesn't matter. Now, some of the ones coming later, you have to be careful on the order. These you do not. The order doesn't really matter much here. Okay? So, any questions? All right. Now we're going to move to reflecting graphs. Okay? Another common transformation is a reflection. For instance, if you consider the x-axis to be a mirror, and then this is your parent function with f of x equal x squared, there it is. But now you negate the x squared. What you do is every value that was up here, you negate it, which flips it across the x-axis, making it look like a mirror. So now there's a function. H of x is minus x squared. That's for reflection across the x-axis, because you're negating the y. All your y's that were positive up here become negative down there. It's a mirror image or reflection of the graph of f of x equal x squared. Your parent function, your square function. You just flipped it across the x-axis. These you have to be a little more careful in what order you do things. So we'll see that coming up later. Though they don't make a big deal about it until they give them to you on the test, and then they try to trip you up. But just be careful on those. All right, so reflections in the coordinate axes, you can either do x or y. Reflections of the coordinate axis of the graph of y is equal to f of x are represented as follows. Reflection in the x-axis is flipping your y, so h of x is equal to minus f of x. Reflection in the y-axis is h of x is f of minus x. There you're flipping the x's, not flipping the y. Make sense? Remember what's f of x? Y. So this is a negative y, and this is your negative x. Okay. And they go kind of backwards. If you negate the y, you're flipping across the x-axis, and then if you negate the x, you're flipping across the y-axis. Which makes sense, too, if you think about it. So here's a function. This is a quartic function. We didn't have this as a parent function, so let me explain it to you. Anytime you take f of x equal x to an even power, it's going to look a lot like that squaring function with these minor differences. Okay? Still has the same y-intercept, 0, 0, x-intercept 2, 0, 0. But what happens here when you raise it to the fourth power rather than the second power, it's steeper on the wings and flatter near 0. So it goes out flatter and then goes up really steep. Flatter here, goes up really steep. Okay? Now, what kind of translation, a reflection do you think you can have here? Maybe g of x equal minus x to the fourth. And what would that do? Flip it down this way. Here's a catch. What if you did f of minus x? Flip it across the y-axis, looks exactly the same. That doesn't make any difference at all, okay, in this one like this. Okay? So that's not an important transformation. That reflection across the y-axis gives you the same function. Okay? But translation, a reflection across the x-axis gives you exactly the opposite. Okay. All right. Now, example 2 is showing you graphs and then asking you what made those graphs happen. Like I said, they like to do it both ways. So each of these graphs below represents a transformation of the graph of L, the graph we just looked at. Write an equation for each of these functions. What do you reckon the A one is? What do you reckon has happened to that? Okay, I heard something, but I couldn't make it out. Oh, very good. You first reflected it, and then you translated it up. So it'd be a negative x. Oh, I'm still green. Okay. I feel like the Grinch. Okay. All right. If I can get my pen to come back. Come on. Come on back. All right. Negative x to the fourth. Then you added 2 to get it to go up there. So in this one, the order matters. You negated first and then went up 2. Okay? All right, what you reckon happened to H? So, let's see. So this is your y is equal to g of x is equal to that. And what, this one? Okay, negative x to the fourth, except, what are you translating here? Yes, so how do you do that? Second? Remember, x's are always, opposite. So the x minus 3 fourth. There it is. That's your h of x. Okay? Now, again, I think it's most important to negate it first. You remember your apparent function was up here. You negate it first, then you shifted right 3. So, negation, then x minus 3 to the 4. Does that make sense? So already we're doing combinations of reflections and shifts. Okay? Let's see how they did. The graph of G is a reflection in the x-axis followed by an upward shift 2 units of the graph of f of x equal x to the fourth. So your g of x would be minus x to the fourth. There's your reflection. Plus 2, there's your shift up. The second one, the graph of h, is a horizontal shift 3 units to the right, followed by reflection. Now you can do that one either order. You could reflect first and then shift, or shift first and then reflect. The first one, you really need to reflect first. This one, it doesn't matter. Okay? And that gave you minus x minus 3 raised to the 4th power. Just like y'all said. Very good. There's example 2, and there is a checkpoint. So please do your checkpoints. All right. Trying to find this verbiage here. Okay, this is the bottom of page 70, which indicates they skipped example 3. Yeah. So we're going to need to go back and do example 3. But I hear noise is going on. How much time do we have? Huh? 9:45. It can't be. Okay? All right. All right. We'll have to start next time with example 3. Okay. Whoa. We got some homework on, don't we? Yeah, I wouldn't want you to leave without homework. Okay. Do any of the odds, either 5 or 7, they're both at Calc Chat. I think you can do 9. It should be at Calc Chat. And then you can do 11 or 13. They both should be at Calc Chat. And then I think you can do any of the odds 15 through 19. They should all be at Calc Chat. 15 should be at Calc View. And then any of the odds 21. Okay, wait. I think we'd better stop there because we haven't gotten to the others. So just go through 19. Good deal. One other thing. Have a good weekend. Of course, working on a quiz will make it a good weekend, won't it? Yes. Okay. So we'll see you on Tuesday.